This video is for my pre-algebra classes over lesson 27, Laws of Exponents. So ladies and gentlemen, what I'd like you to do here is drop down about 5 spaces. So 1, 2, 3, 4, 5 spaces. And then below that, we're going to make a nice wide 2-space big rectangle. And you may be able to anticipate what's coming, maybe not. But what was the first thing that we learned how to do in math class? Remember, not counting. We should have learned counting before we got to math class. Now, hopefully you just said addition. We learned to add. And remember that addition is really repeated counting. So if I say 3 plus 5, I'm saying, okay, start at 3 and count up 5 more. Well, 3, 4, 5, 6, 7, 8. That's why 3 plus 5 is 8. The next thing we learned in school, in math class, was we learned to undo addition. We learned subtraction. We learned subtraction. Eventually, we built off of this skill and we learned that if we keep adding up the same number and over and over and over again, we can express that as multiplication. One of the next skills we learned after multiplication, which is really repeated addition, was we learned to undo multiplication. We learned about division. After a bit, we built off of this skill as well, and we found out that if we repeatedly multiply the same number, well, we don't have a nice new table to memorize like we had our addition tables and our multiplication tables. We at least have a way to write that repeated multiplication in a shorter form. And we learned about exponents. And so what we see here is addition is repeated counting, multiplication is repeated addition, exponents are repeated multiplication. So if I were to split my pyramid here that we've just built in half, everything over here is really just something else repeated. We learned how to count, and then we learned repeated counting is addition. We learned to add, then we learned that repeated addition is multiplication. We learned to multiply, then we learned repeated multiplication is exponents. On the other side of the pyramid, we learned that we're undoing things. These are called inverses. So the inverse of addition, what undoes addition, is subtraction. The inverse of multiplication, what undoes multiplication, is division. So up here should be the inverse then of exponents. What undoes an exponent? And hopefully you've just said roots. If you said square root, you're not completely wrong. You're just being too specific. Remember that a square root specifically is the inverse of squaring. So it's only one kind of root that would cancel out one kind of exponent. So in general, the inverse of exponents are roots. So from our pyramid, we can see some connections that lead to various different properties. What I want to focus on here today is that whenever you perform an operation on powers, so powers means it's got a base, it's got an exponent, the whole thing all together is your power. So x to the 5th power, that would be a power. So whenever you perform an operation on powers, so like we multiply powers, we do a power to a power, we divide powers, comma, you can instead do the operation on the step directly below to the exponents. So if I am multiplying powers, I have a power times a power. Instead of actually multiplying them, I can just combine them and instead, one step below, add the exponents. And that, ladies and gentlemen, is a property called the product property of exponents. And symbolically, this would show up as x to the power of a times x to the power of b equals x to the power of a plus b. So ladies and gentlemen, in order to be able to read this properly, you need to be able to do some very simple compare and contrast. I like to say that we need to do some comparing and contrasting on the level of a kindergartner. And that might be exaggerating it a little bit, but it's very easy to overthink this. So if we treat the equal sign as dividing this up into two different sections, just compare and contrast. What do we see is the same? What do we see that's different? So one of the things that, in my opinion, a kindergartner would notice right away is that we have x's here, and we still have an x over there. So that tells me something right there algebraically. It means that whatever my base is here, it has to be the same thing here, and it will be the same thing here. So we have to have the same base, and we will still have the same base when we're done with this property. So the base isn't going to change. So that's very important to using this property. If you do not have the same base, you may not use this property. The other thing I'm going to notice here is on this side of the equal sign, there's an a and a b. Those are not the same. Which means in algebra that those two exponents do not have to be the same. If they had to be the same, we'd use the same letter like we did with the x's. By using two different letters, this means they could be the same or they could be different. A could be 2 and B could be 2, but they don't have to be. A could be 2 and B could be 3. So by using different letters, we have the freedom to use different numbers. The other thing I notice here is I have two x's here, but just one over there. So we go from having two powers to one combined power. Another very simple compare and contrast. Here I have a multiplication between the two powers, whereas over here I have addition between the two exponents. So those are all things that we should notice from this property. So take a highlighter. I don't really care what color you choose. I'm choosing my blue here. Let's make this pop out a little more. So let's practice this. Let's say I gave you the problem x to the third power times x to the fourth power. So first of all, do we qualify for having the same base? Yes, we do. So then what we should be thinking in our minds here is that this is going to be x to the power of, well, a plus b, so 3 plus 4. Now remember, red is our thinking, so I'm not going to make you write this step out on the homework, but you should be thinking it, that this becomes x to the power of 3 plus 4, and that's probably going to go through your mind in all of half a second before you realize that it's x to the 7th power. All right, for our next example, let's check out x to the third power, y to the second power. X to the third power, y to the second power. So if I use the property here, okay, well I got an exponent 3 and exponent 2, so an exponent of, well, 3 plus 2 is 5, right? No. Hopefully you've caught the issue. We must have the same base. Do we have the same base here? No. X and y do not have to be the same, which means that we cannot combine these. Which means This is as simplified as it can get. There's nothing that we can do with that right now without more information. So that guy's all done. All right, well, let's say I have that x to the third power, y to the second power, but instead I'm taking this pair of powers and I'm multiplying it by this pair of powers. Well, in this case, since this is all multiplication, all of this is multiplication, we know that multiplication is commutative and associative, we could rearrange this to put the x's together with the x's and the y's together with the y's. So let's cut to the chase then here. We know, if we're thinking about this, that this is going to combine to just one x power, but it's going to be the 3 exponent plus the 5 exponent. And I know that this is going to combine into one y power, but it's going to be the 2 exponent plus the, well, if we don't have an exponent there, what is its exponent? Well, hopefully you remember that there's always an invisible 1 exponent. So that's really y to the first power. So this will be 2 plus 1 for my y value, or my y exponent. So 3 plus 5 gives me x to the 8th. 2 plus 1 gives me y cubed. X to the 8th power, y cubed. All right. Next example, let's say I have 2 to the third power times 2 times 2 to the 7th times 2 to the 4th. Now, noticing that all of these have the same base, we can go ahead and extend the property to combining multiple powers into one combined power at the end. So this will just combine all into one power of 2. Add up the exponents. I have the 3 plus the invisible 1 plus the 7 plus the 4. And if we add that up, 3 plus 1 is 4, plus 7 is 11, plus another 4 is 15. So this really all comes down to 2 to the 15th power. And now this could be an acceptable answer depending on what the problem is asking for. If the problem is asking for you to express your answer as a power of 2, then that would be your final answer. If the problem is asking you to write the answer in exponent form, again, that's your answer. If not, then we should probably pull out our calculators and save ourselves the time of multiplying 15 2's together. So if we go ahead and grab our calculators and type in 2 to the 15th power and hit enter, we will discover that this is 32,768. So make sure that you can get that on your own calculator. If not, you're going to want to come see me and ask me questions about that. All right, ladies and gentlemen. So that's if I'm multiplying a power, I can add the exponents. But what if I'm dividing powers? Well, if I'm dividing powers, I can instead subtract the exponents. And that is our next property. Our next property is known, instead of the quotient, or excuse me, the product property, it's known as the quotient property of exponents. And so in this one, we typically express division as a fraction. So x to the power of a over x to the power of b equals, well, if we divide powers, we can instead subtract the exponents. So a minus b. So again, we notice we need to have the same base. The exponents do not need to be the same. And because we're dividing the two powers, we can combine it and subtract the exponents. Grab a color, new color. I'm going to choose my green here. New property, new color. So in this case, if I have x to the power of 4 over x to the power of 3, then we would think of this as x to the power of 4 minus 3. Which of course 4 minus 3 is 1, but I write that in red because are we going to actually write x to the power of 1? Well, no. Just like we had y to the power of 1, we just wrote as y, and 2 to the power of 1 really was just 2. X to the power of 1 is really just x. We're going to simplify that down to just x. So let's say we have a to the power of 5b squared over a cubed b. So first things first, remember that b is really b to the first power. So hopefully you can see that red there. And so then we're combining the a's with the a's and the b's with the b's. So for the a's, I've got a 5 minus a 3. And then for the b's, I have a 2 minus a 1. And so if we simplify this then, a to the 5 minus 3 really is a squared, or a to the second power. And 2 minus 1 is 1, so I'm not going to bother writing that. I'm just going to write b. b to the power of 1 is really just b. And there it is. Now, ladies and gentlemen, let's say we had a problem like this. 2 to the 7th power times 2 over 2 to the 3rd power times 2 to the 4th power. Now, there are many different ways that we could simplify this, and ultimately this is going to come down to a combination between our two properties. We're going to use some product property, we're going to use some quotient property of exponents. Now, my recommendation would be to take this as a numerator and then a denominator and then divide. So if I just look at the numerator, I've got 2 to the 7th power times 2, which is really 2 to the first power. So 7 plus 1 gives me 2 to the 8th power. In the denominator, 2 to the 3rd power times 2 to the 4th power, well, 3 plus 4 is 7. And then I finish this off by dividing. Dividing means I'm going to minus or subtract my exponents. So 8 minus 7 gives me just a 1. So 2 to the first power, or 2. All right, let's flip over. Well, actually, before we flip over to the back, one more here. Let's say we did a power of a power. So we take a power and raise it to another exponent. Then instead of doing that, we can go and multiply the powers, multiply the exponents. So that is what's known as the power property of exponents. Symbolically written as x to the power of a, that's my power, and then raised to a power. So raised to the power of b. And so instead of doing a power to a power, I can go one step below on my pyramid and instead multiply the exponents. So that'll just be x to the power of a times b. Grab another color. I'm going to grab my purple. So if we try this out here, I'm going to have x to the 3rd power, and then let's raise it to the 4th power. So if we have x to the 3rd power and then we raise it to the 4th power, we should be thinking that this is really x to the power of 3 times 4. And of course, 3 times 4 is 12. If I had 10 to the power of 7, and then we squared it, then we would be thinking here that this is really 10 to the power of 7 times 2, which of course 7 times 2 is 14. 10 to the 14th power. Let's say I had a to the 5th power, b to the 2nd power, c to the 4th power. and I raise that all to the third power. Now here, because we're multiplying all these together, and multiplication is right underneath exponents, our third power here is basically going to distribute to each one of these powers. And so this will become a to the power of 5 times 3, b to the power of 2 times 3, and c to the power of 4 times 3. Try to get that on my shadow there for you. So if we go ahead and do this then, this will really be a to the 15th power, b to the 6th power, and then finally c to the 12th power. There are two more exponent properties that we're going to take a look at here, but these we're going to deviate from our pyramid just slightly to take a look at this. We're going to use the properties that we've done, but these are a little bit different. So first up, let's simplify the example x to the 4th power over x to the 4th power. If we use our quotient property of exponents, we know that this will become x to the power of, and then we subtract the exponents. So the power of 4 minus 4. Well, 4 minus 4 is 0. However, if we do this problem again and just use our common sense, x to the power of 4 divided by x to the power of 4, something divided by itself we already know is 1. And so what we've discovered here is that x to the power of 0 turns things into 1. And that may seem counterintuitive, that may not make a lot of sense. So what I have to say to you first and foremost is accept it. Sometimes we may run across a concept that we have to accept as true, even if we don't understand why it's true right now. And over time we work at understanding it. But first things first, accept it. Even if you don't understand why right now, it is true. Now, to try to help you out with that a little bit, there are tons of different ways that you can come at this and think about it. But one way that you could think about it very quickly here is, if I asked you what x to the 4th power meant, you would tell me that it would be the same as multiplying 4 x's together. So x to the 3rd power would be multiplying 3 x's together. X to the 2nd power would be like multiplying 2 x's together. X to the 1st power is like having a single x. Now remember, we're thinking multiplication. So it'd be like multiplying by a single x. So if you have an exponent of 0, that's like, what could you multiply by? Whereas if it's as if you didn't multiply at all. Well, that's 1. Multiplying by 1 is the number that you multiply by when you want it to be as if you didn't multiply at all, because it doesn't change anything. So 0 in the exponent doesn't change anything. Multiplying by 1 doesn't change anything. That's one way to think about it. Again, there are many others. So this is what's called the 0 rule for exponents. And it actually comes with a little disclaimer. It starts off with for x not equal to 0. So you can't have 0 here. If you try to do 0 to the 0 problem, the trouble that we run into is 0 to pretty much any other power, well, most of the powers, at least the positive half. 0 to anything positive is going to just be 0. So 0 to the 0, from that perspective, should be 0. But if x is anything else, then raising it to the power of 0 should be 1. So should it be 0? Should it be 1? There's not really a good answer there. And so it's just not allowed. We don't do 0 to the power of 0. Not allowed. You can do anything else to the power of 0, but not 0 itself. So grab another color highlighter here. I'm going to go with my orange this time. You don't have to go with orange. Normally if I do orange, you're supposed to match me, but this time you got a choice. Just grab a new color. All right. So if I gave you y to the power of 0, you would tell me that the answer then is 1. So long as y is not 0. So y does not equal 0. So that's a little tiny for you to read. This says y not equal to, so it's equal sign with a slash, 0. If I asked you what is 2 to the power of 0, you would say 1. Nice and simple. If I asked you what is a to the 5th power, b to the 2nd power, c to the 4th power, all raised to the power of 0, you would say 1. Although secretly, you're also thinking, so long as a is not 0, b is not 0, and c is not 0. Because if any one of those was 0, then when you multiplied them together, they'd all become 0, and then you'd have 0 to the 0, and you're not allowed to do that. So as long as they're not all 0, or none of them are 0, we're good to go. So what if I had x to the 2nd power, y to the power of 0? Well, in this case, if we think about this, this really would be x squared times, and then y to the power of 0 would turn into a 1, so long as y does not equal 0. Well, and then 1 times anything disappears, doesn't it? So really, x squared y to the power of 0 would simplify down to just x squared, as long as y isn't 0. And then finally, what if I did try to do 0 to the power of 0? Well, the answer would just be undefined. And we'd say, move on to the next problem. All right, throw another line across your paper here. Last thing. Let's say this time I had x cubed, and that is over x to the 4th power. Well, again, if we use our quotient property, then this will be x to the power of 3 minus 4, which of course 3 minus 4 gives me negative 1. So this will be x to the negative 1st power. But let's explore this again. X to the 3rd power over x to the 4th power, but this time let's look at it by expanding it. So x to the 3rd power would be x times x times x, which normally we wouldn't need the dots, but I'm just putting it in there for emphasis. On the bottom I would have x times x times x times x. Now of course, we could reduce before multiplying. So an x on top would cancel an x on bottom, x on top would cancel an x on bottom, x on top cancel an x on bottom. Now remember, when these cancel, they're not really truly canceling and disappearing, they're technically becoming 1s. So up top now I've got 1 times 1 times 1 is 1, and on bottom I have 1 times 1 times 1 is x. Now very commonly students see 1 over x and think that they can just make it x. No. When x is in the denominator, x is in the denominator. You can't just flip it up. However, if you think about the variable x all by itself, if you were to turn that into a fraction, you would turn x into x over 1. So if we look at the relationship between turning a variable like x into a fraction, versus this, we discover that what we've gotten is the reciprocal of x. This is the reciprocal of x. But that's equal to x cubed over x to the fourth power, and that's equal to x to the negative first power. And so, ladies and gentlemen, we've discovered that the negative first power creates reciprocals. Now, reciprocals, if you have a whole number and make a reciprocal out of it, you've got a fraction. And fractions mean division. And so essentially, what a negative exponent does for us is it gives us repeated division. So the negative is an opposite. So the opposite of repeated multiplication is repeated division, but written as a fraction. So, ladies and gentlemen, this is what's called the rule for negative exponents. And again, it says for x not equal to 0. Now this time it says that because if you think about if x is 0, you're not allowed to have 0 in the denominator. No zeros in the denominator. So we got to avoid that. So x can't be 0 here. X to the negative first power equals the reciprocal 1 over x. Now, with this being said, I'm going to extend this property a little bit for you and generalize it. So if I were to give you x to the negative n power, so where n is something other than 1, well, it could be 1, then in general what's going to happen here is that negative will still produce a reciprocal. But what's going to happen is in making the reciprocal, that negative gets used up. So the negative turns this into a reciprocal. So n will still be n, but the negative disappears when I do my reciprocal. So real quick here, some examples. If I, grab your, let's put a period on there actually, and grab your last color highlighter. All right, and so examples. First example, let's do 2 to the negative first power. Real simple, just what's the reciprocal of 2? Well, 2 would be 2 over 1, so flip that over, or invert that. It's 1/2. 3 to the negative first power would be 1/3. If I were to do x squared y to the negative first power, this would be, well, that whole thing now, since it's grouped together in parentheses, would become my denominator. So this would be 1 over x squared y. If I had x to the negative third power, the negative again is going to give me my reciprocal, and it'll get used up, so it'll just be 1 over x to a positive 3. If we apply that to a number like 5 to the negative third power, that would become 1 over 5 now to a positive third power. There's then, of course, 5 to the third power. 5 times 5 is 25, times another 5, 125. And that, ladies and gentlemen, is the end of our lesson.